There it is. All right, welcome everyone, and welcome to this last ZX seminar of the year. Today we have Nicklas Botö, who will talk to us about the Zeta calculus. He loved the calculus with observables. So, Nicklas, please take it away.
Thank you. So what we will present today is a part of a master thesis that Fabian and I did at Chalmers University in Gothenburg, Sweden. You can find the thesis at this website if you're interested in reading the whole of it. We were supervised by Robin Adams at the computer science department. There are some parts of the thesis that are left out for this talk, which I don't think are very interesting to the ZX crowd. Some higher models of the language, philosophical investigations, and some technical problems, which we'll just cover shortly later. For a quick overview of what we will talk about today is that we begin with a bit of what non-linearity is in quantum programming and talk about kind of the basis for our work, which is in the internal languages for symmetric monoidal categories. Then we define the Zeta calculus with this categorical language. We will look at how you can use this for quantum programming in a certain model. We will discuss the main strengths of this language and some weaknesses and how these are possibly mended in the future before we conclude. So usually when we talk about quantum programming, it's thought of as linear. And why is that? Well, it's usually justified by the no cloning theorem, the fact that you can't create a perfect and independent copy of some arbitrary quantum state. And it's time reversed dual the no deleting theorem. But some other languages, the first one I can think of being QML, have interpreted the duplication of variables in quantum programming not as this perfect cloning, but rather as sharing, where we spread the amplitudes over a larger quantum state. This doesn't create perfect copies, which is why it's still physically realizable. It just creates possibly entangled copies of these states. And still, if you do interpret copying of variables like this, you might want to limit it because this is in some sense an implicit production of entanglement that makes it a bit more difficult to reason about these programs. So if you're designing a language in the functional paradigm, usually this is mended by linear type systems, where you say that the variables can be used exactly once, or affine languages in some senses where they can be discarded as well. And if you want to include classical data, you can also use type exponentials, where these are certain types which you decorate that can be duplicated. And what we will argue here is that this puts some constraints on expressiveness, that these languages, when you program in them, especially if they come just with a predefined gate set, tend to look sort of like circuit description languages more than anything else. And therefore we want to investigate how can we use non-linearity in more creative ways. So the work that we're building on mostly is this internal language for autonomous categories by Mackey. And when we say autonomous here, we mean symmetric monoidal closed. So what they've done is they've created a term language for the multiplicative fragment of linear logic. And what this looks like, if you view it as a programming language, is a linear, simply typed lambda calculus with products and units. What they show in the paper is that is precisely what is needed to describe closed symmetric monoidal categories. So we'll begin by looking at this syntax. Of course, we have variables, abstractions, and applications, just the standard definition of a lambda calculus. We add to this products and some elimination of products in the form of let expressions, as well as the units and some elimination rule for units as well. The type system of this has, of course, the variable typing rule, but since this is a linear type system, the only structural rule that we have left is that of exchange. So contraction and weakening that are usually found in nonlinear type systems are omitted. We introduce a unit type I, which you give to the unit term. And also we have this elimination rule for it as well, that if some term M is of the unit type, we can discard it for some term N instead. Then we have pretty standard rules for tuples, let expressions, and of course, function types as well. The way we interpret this categorically is that we map every base type of the language into the object set and every base function symbol into the hom set of the category. And then we extend it with these types we saw before. So the unit type is mapped to the designated unit object of the category. The product type is mapped to the tensorial functor, and then function types to the internal hom set or hom functor. Then in this type system that we saw, every valid judgment that gamma gives m the type A is mapped to some morphism in the category. So the contexts are interpreted as the folding of a tensor product on the interpretations of the types in the context. So we have this morphism. I think this semantics will be a bit more clear later when we give the semantics for our language, because then we do it instead in string diagrams, so we can look at them specifically. So onto the Zeta calculus. To be very clear with our language, we will move from closed symmetric monoidal categories to compact closed instead. In one sense, to be closer to the Zeta calculus, and also to make these diagrams a lot easier to read. But unlike the Zeta calculus, we do not have the dagger structure, and this is some future work we will discuss later. So first, for some background of the categorical machinery behind the Zeta calculus, we have in a dagger SMC that an observable structure is this triple, consisting of some object, some co-multiplication, and some co-units, which we draw in a diagram like this and this. Subject to these first three laws, saying that's a cocommutative comonoid, as well as the Frobenius law and speciality. And what is widely known is that this is corresponding precisely to an orthonormal basis or an observable. Since we're not working with the dagger structure, we will instead prefer this definition, where we have both the co-multiplication and co-unit together with the multiplication and the unit, such that this pair is an internal cocommutative comonoid, or this is an internal cocommutative comonoid, this is a commutative monoid, subject to the previous laws. And from this point in the talk, I will talk about cocommutative comonoids or bases or observable structures somewhat interchangeably, I hope without confusion. So the minimal extension we can make to the internal language of SMCs for our purposes here looks like this. So we define a set of symbols, Bercano, which are representing the bases or observable structures. And then we define the syntax of the Zeta calculus as this set algis. And coincidentally, this rune algis is the rune for Z, and also looking like a spider, which is nice. And the extension that is happening here is that every rule or syntactic construct that introduces a variable will also be decorated with some symbol zeta from these set of bases symbols. So we can compare the, for example, zeta abstraction to the lambda abstraction of the internal language here. That this has this decoration. And this is also true for the rule of let expressions, which introduces two variables. Otherwise, it's the same. To make this a bit more fitting for quantum programming, and also to capture more of what we think the Zeta calculus is about, we've added a few more syntactic constructs. We define for each basis symbol in Bercano a set of unbiased point symbols, and then we can decorate the Zeta abstraction with some alpha here. In a more concrete model, this would represent, for example, the rotation defined by an observable, so the rotations on the block sphere. We also add states, effects, and scalars, where we call a morphism going from the unit type a state to the unit type an effect, and from and to the unit type a scalar. We add this in the language by this construct here. So call it a generator, and it's defined by a basis, some integer, where the negative numbers represent effects, the positive sized states, and 0, a scalar. We will see later that this is actually quite a nice addition. We can define compass structures, entangled states, useful things with this later on. So the full syntax looks like this. Quite similar to the internal language, with variables, units, generators, Zeta abstractions, application, tuples, let expression, and unit elimination. To define the nonlinear type system, we first have to get this out of the way, which is the definition of the set of types. We define this over some base type T. Canonically, when working in this quantum model, this would be the type of qubits. So C2, for example. And other than that, the types are the unit type, the product type, and the function type. And here we're chosen to use the normal function symbol instead of the lollipop to designate that this is nonlinear. We define size types as a fold with tensor product over the base type, where 0 is unit type, 1 is the base type. The positives are just this n-fold product, and the negatives are n-fold products into the unit type. Importantly then, the contexts of this type system are also extended by observables. So we define a context to be typed variables, a list of type variables, but also every type variables come with a basis denotation here. So now we try to connect this basis denotated syntax with the type system. Wherever a variable is introduced, we have this basis, and every type variable is decorated with a basis. So in these typing rules that affect it, we connect them. And principally, this was the rule for function types and let expressions. So we see in the function type rule that if we have a Zeta abstraction, we extend the context of the variable x and basis decoration Zeta. And also similar here in the let expression, that we extend the context here with these variables in the basis Zeta. So this is the full set of typing rules. The only thing more that we haven't covered is this rule for generators, where we use the size type to define the type of this. What we've seen so far is purely linear. We haven't touched upon the structural rules of the language. And of course, this is what we want to investigate since we want to have a nonlinear type system. So to add the nonlinearity, use this fact that every typed variable has a basis decoration. So for the rule of contraction, we can duplicate this here. And the rule for weakening, we can discard it. So the intention of this is contraction uses the co-multiplication of the observable, weakening uses the co-unit. And then this is the full set, where we just added the structural rules of contraction, weakening, and exchange. We will describe our semantics in string diagrams following largely the conventions of interacting quantum observables by Botö and Duncan. So for example, we have that the unit wire is the identity morphism. We have cups, caps, units, symmetry. This is what we denote with the face group. These are the right-hand side of a spider, co-multiplication, and co-unit. The only difference being that since the string diagrams represents these judgments, the left side, the open input wires, will be typed variables, and the right side would be just types. So this would be how interpretation of some judgment would look like. So for the atoms of the language, we have that the variable typing rule is simply this identity wire. And these generators are simply this, some right-hand side of spider, which might have the dual types instead, since it's the compact category, and that would be an effect. The rule for abstraction is the one that uses compactness. So we say that if this term M can be typed within the context of gamma, extend with X zeta A to the type B, then we can just reverse this wire into A star. And also here is where the face group of some observable is used, where we have the alpha denotation coming into play here. Application is just the dual of this compactness, that if we have some term M, which is a function type from A to B, then we can just bend the wire from some input into this. Tuples are quite silly, just place them next to each other, the interpretations. The let expression, where we can split some type some product type M and feed it into one of the context inputs of N. And also units, where the unit term is an empty diagram and where the unit emulation just uses the uniters of the category to discard the unit type that's produced here. So the structural rules making this nonlinear use, just like we said, the fact that if you want to define weakening, that we can type some term M in the context gamma to B, then we can also type it in some extended context. Since every variable has decoration with its basis, we can use that basis co-unit to discard this variable. And contractioning instead uses the commultiplication here to be able to extend the context with two variables. So for an example of an interpretation that we can look at here is this one, which is a very simple just sharing function. So this is a term which takes in a variable x in the zeta basis with some rotation alpha and produces two copies of this. Then we have this type derivation here that we can use contraction on, or the abstraction typing rule, then contraction to duplicate this into two, and then type these two of the tuple separately. And since we define the semantics by induction on these derivations, what we do is that we label the diagrams with the rules that are applied. So the outermost rule is the B rule, and then C, T, V, V. So we get that the interpretation of this typing derivation is a diagram that looks like this. When discussing
Sorry,
specific...
can I ask a very basic question? You're calling these things derivations, but to me it just looks like you're constructing a diagram. So
Yes,
diagram is a derivation? That's what
a diagram is a derivation, yes.
So it's not rewrite rules on the diagram, it's like a derivation.
No, it's not the rewrite rules. So this is, for example, this is a typing derivation, of course, of some term here, where we get this type T to T product T. And this, we define the semantics by induction on this derivation tree, and then we get this out of it.
Okay.
So you see that the first rule here is the B rule, and then we just have induction inward until we get the whole term. So from this derivation, we get this diagram.
Yeah, I see. Okay.
So when we're talking about quantum programming later, we want to kind of look at how these terms act more naturally. And when we talk about this quantum programming, we will almost exclusively look at closed terms, which are terms that have no free variables in them. And this means that they can be, their types can be derived in the empty context. So their interpretations as diagrams would just be no open input wires. But to actually look at how these would look as functions, we want to externalize them, that is, reverse their input wires. But since this language allows higher order functions, we might want to look at how they act on them as well, which is why we define this procedure. So if M is some closed term, we define D to be the interpretation in the empty context of that term. All the higher order arguments are supplied with boxes, and then we reverse all the wires of dual type and remove the labels. And this is quite difficult to understand like this, so we will look at some specific example. So it's one of the simplest higher order functions, which is in Zeta, we introduce the variable f, and then we self-compose f. So if you have the diagrammatic interpretation of this type derivation, it looks like this. And we have one higher order argument here. So we simplify the diagram, and we place a random or arbitrary function box f as its argument. Then we have one dual type input wire left, which we just reverse and remove the labels. And then we simplify this to get something like this. Then we can talk about that the externalized form of this zeta term is a diagram which looks like this. And if you want some intuition on what this means, which is by no means applicable to all types of diagrams, but something like this. This should be a function that in the basis zeta composes the function f with itself. which we can look at as a variable coming in here, passing through the function f, looping around, going in once more, and then out. And now we'll move on to specific models of this, or instances as well. What we mean by saying instance and model is that instance is a syntactic notion. We have a finite set of symbols for the bases, zeta and psi, for example. For each of these bases, we have some observable point symbols. So for example, the rotations of z and x, all these symbols. And we denote it like this. A model is a syntactic or semantic notion, sorry, where we mean the following. We have some concrete category C, which will canonically be the category of finite dimensional Hilbert spaces. Some set of observable structures in that category, Z and X, for example, and we denote it like this. And also we have a few notational conventions, which I hope will be quite familiar to the ZX user. That if we have the unit of some observable structure, this is a part of the unbiased points. So if you denote a Zeta abstraction and its unbiased point with the unit, we simply don't write it, which is equivalent to the fact that we omit zero face of spiders. Compact structures, so essentially cups and caps with a spider on them, will be written as eta dagger and eta. And they can be constructed for some basis just by this zeta of 2 outputs or zeta of 2 inputs. But in some models, they all coincide. For example, in ZX, these coincide. So we just write eta and eta dagger without the basis decoration. And finally, when we have linear terms, so if a term doesn't duplicate or doesn't discard its variables, then the co-multiplication and co-unit are not used. And then we can simply write lambda instead, because it doesn't matter which basis. So on to actual quantum programming. We define the quantum model of the Zeta calculus by concretizing it in finite dimensional Hilbert spaces with the observable structures zeta and psi. And this should be familiar as just the red and green spider of the ZX calculus, with the corresponding phase groups and unbiased points looking like this. And the intuition, of course, is the rotations around the block sphere. Since these are semantics in ZX diagrams, we employ some of the same kind of simplifications. So for example, we assume that there's a term Hadamard, which can be constructed in the language, but we just write its interpretation by extending the language with some Hadamard blocks. And like we said, all the compact structures coincide. So we will not use a compact structure for Z and one for X. We'll just write eta and eta dagger and draw them as cups and caps. So for some hopefully simple example terms in this model of the language, we have the rotations of Z and X. So this is a function which takes a variable X in the Z basis with some rotation alpha and then just returns X, which is just a unary rotation spider. And the same with the basis Xi, we get the unary rotation spider in X. The simplest sharing function is one that takes a variable X in the Z basis and produces 2 copies, which looks precisely like the co-multiplication. So 1x coming in here, 2x coming out in the Z basis. And also we can define a gadget, which we'll use later to actually define phase gadgets in this language. So this would be that we take a variable X in the X basis, corresponding to the input here, to the red spider. Then we produce 2 instances of X, the 2 outputs. And then we give one of the X's to an effect in Z with a rotation alpha and return the other. So 1 to here and 1 out. What is quite surprising and quite cool, I think, is that we can actually define control gates and multi-qubit gates with this quite minimal language. That we don't need a predefined gate set for this, and we don't need some control structures, like a quantum if statement or something, to define them. So the C0 gate, for example, can be defined quite minimally in this language. So we have the control variable c introduced in the z basis, and the target variable in the x basis, corresponding to the c coming to the green spider here, and t to the red spider. We produce 2 copies of each of them, and then we give c and t once to a cap. And then, since this returns a unit, we eliminate that and return c and t in a tuple. So c and t coming here, one variable is shared into the cap, another into the cap here, and then we return them. So we can construct the C0 gate in this very minimal form. We can build upon this intuition even more. So we use the fact here in some sense that we can link variables together, or shared instances of a variable in different observables. So we can define what we call the linking function. So this is just some completely linear term, which takes a function f and a tuple of x and y, and then applies f on the first variable and sends this tuple into the cap, with interpretation looking like this. And we write L sub f for this, LF. So for example, the CZ gate can be defined in this way. We have x and y variables introduced both in the Z basis. Then we link x and y, the Hadamard gate, and return another pair of x and y. So we used sharing in these bases and then link them together with the Hadamard, which looks like the CZ gate. And also phase gadget, since we defined the term g of alpha before, we can introduce x and y in the Z basis and link them together with this gadget function and return x and y, giving us a term like this. More generally, this just means that we can control entanglement in some sense. We can link shared variables together and control how they interact. So for example, if we have the most general term, just 2 variables in separate bases, we can link together with some function and then put them into the term m, giving something like this. So this would in fact be a very quantum specific programming technique that shows up in this language. And you can also stack them together. So this quite complicated looking term really becomes quite natural when you look at it beside the diagram. We introduce x, y, and z in the Z basis. We link x and y with a gadget. Then we link x and z with a Hadamard. And then we return y and z flipped, which is precisely what is happening here. We have x and y, they're linked with the gadget, x and z linked with the Hadamard, and then swapped. Since our language also admits the possibility for higher order functions, it is fun to investigate what that means together with the sharing in these different bases. So if we take the simplest example of a sharing function, just taking some variable f and produces 2 copies of it in the basis, we get the diagrammatic interpretation here, which looks like the one before, but instead we have the function type here. Because of the compactness of the category, we can expand these into singular unit, or sorry, base types of this model, the qubit type, looking like this. Then we perform this externalization, that we have the first higher order argument, which we place a box on, and then simplified it like this. So we see that the sharing of a function is something which looks like this. Some other higher order function examples are, we can use higher order sharing on the sharing function itself, for which we get this nice looking diagram here. Self-composition, which we looked at before. And we can extend this even further to get the parallel function, which is just self-composition, where we have some function f, which is interjected into the composition, getting something like this. So a fun example we thought of a higher order function, which is quite unexpected when you don't look at the static calculus in a very functional programming way, is this, what we call the Pauli switching function, an instance of the parallel function. So we define the switch in beta to be taking in some, where beta is one of these bases, to be the function f, which we then compose with itself with a Hadamard in between. And we call it the Pauli switching function because it acts funnily on Pauli gates. So if you have the switch of zeta in a poly Z gate, you just get the identity wire. And the same for x, you get the identity wire. But on complementary bases, it does nothing. So in general, this function is involuntary, and in complementary basis, it's idempotent. So on to discussing what this means. One large reason that we did this master thesis was that we wanted to investigate nonlinearity in functional quantum programming languages. And as we said before, we think that this is more expressive. Well, of course, it is. The linear language is a subset of the language we defined. And we said that some arguments against it might be that it produces unwanted side effects that you can't control where entanglement is produced. But still, allowing this, we think, creates interesting types of techniques that we can use. For example, this interaction with higher order functions. It doesn't, of course, act like sharing in the classical case that you get separate copies of these functions. But we saw that that's maybe not how it should be used. Rather, you can produce interesting modifications on the functions when you use sharing with them. And other techniques which are at least novel to us. For example, these linking functions, where you can control the entanglement between variables in a quite unique way. And you can do other investigations, for example, like the diagram we see on the right. This is an investigation or analysis of how sharing looks. So if we take the simplest sharing function and apply it to some arbitrary quantum state when it's defining complementary bases, we can investigate the entropy of entanglement that's produced and get a very nice diagram like this. So we can see that the classical points are down in the valleys here, and then we get a lattice of maximum entanglement produced by the sharing terms. Another thing that we wanted to capture in defining this language was complementarity in some sense, because we thought it was interesting what complementarity really means for a programming language. A start of this, we think, is this that we can have the explicit control of which bases you define variables in. This opens up at least the ability to use the complementary observables in the language itself, like in the ZX calculus. So to fully actually utilize complementarity, for example, by these rules of Hopf and bialgebra, we would like to have the whole structure of the Dagger special commutative Frobenius algebra available to us. But since we're not working in the Dagger category, we haven't really managed to do this fully. We saw that the structural rules of the language, contraction and weakening, are the ones that actually use the co-multiplication and co-unit of the observable structure. But with the Dagger functor, this would sort of mean that we have a co-structural rule, so the time-reversed dual of the structural rules. And then what these rules of Hopf and bialgebra would say is actually the interaction between structural and co-structural rules in complementary observables. So for example, the Hopf rule would say that we have a co-multiplication, which is the contraction in one observable. And then a complementary observable, we have the co-contraction. And then this would correspond to the co-unit and unit, or weakening and co-weakening of complementary observables. We think this would be a way to kind of further be able to integrate complementary observables into quantum programming, into a language. Data structure is another interesting thing we thought about in this regard. The ability to, if the language sort of natively supports this control of bases or observables, to be able to define data structures themselves with regard to some observable. And then they would interact interestingly with these Zeta abstractions, for example. We would get in a sense that there are two classical programming languages in one, and that they interact with each other, and that interaction is what creates the quantumness of the language. By this, I mean, for example, that you define some data structure in one observable, then it will be a classical point for the complementary observable. So if you have a data structure defined in the X basis, then the Zeta abstractions of the Z basis would, of course, behave classically. And then the interaction between them would be quantum. The generality of the theory is something we would also like to discuss, that we defined this not specifically just to capture the ZX calculus, ad hoc, but rather went for the categorical description that underlies it. So we noticed that the specific model, which is very similar to the ZX calculus of FD Hilbert ZNX, is useful for quantum programming. But with this generality, does this actually allow any more interesting models? In some sense, it might. For example, the W spider can be added. We can use the fact of it being a cocommutative comonoid to also add it into the language, which we haven't investigated a lot, but it is possible. More generally, it's any SMC with certain internal structure that can be used as a programming language in this way. But the question that we feel mirror the question of if the Zeta calculus's categorical description is useful is if the ZX calculus's categorical description is useful or not. So these kind of general machinery behind it with observable structures and phase groups and compact structures, if that is useful, I think that is mirrored in the Zeta calculus because its definition is so similar. One of the big problems that we have for future work is of reduction. So the usual notion of beta reduction in lambda calculi is difficult because precisely of non-linearity. We define this term of commutation with sharing over a basis to try to reason about this. Where commutation with sharing over a basis is that a certain term can just pass through the spider or the co-multiplication. And then we can define beta reduction by just saying that, well, this zeta abstraction applied to some term reduces precisely when n commutes with sharing over zeta. But the problem with this is reduction depends on the model then. We can't reason about it abstractly as we want to. We don't really feel that this is a problem for quantum programming. Since quantum programming would happen precisely in a model, you can just translate these to ZX diagrams and then use optimizations and compilation from there on. But if this is supposed to be a general theory about quantum computation, then yes, these things have to be solved. And it would also make for a nicer language in general. To conclude of the future work, we would like to move to dagger symmetric model categories using the dagger functor, partly because we want to utilize all of the observable structure. We want it to help to define the reduction relation, hoping in some sense that the completeness of these ZX equational rules can be embedded more nicely into our language. The dagger lambda calculus of Philip here is one thing that we can use to help us along the way. There have been similar things done in regard to the dagger functor. Also, an actual implementation of the language would be nice. We don't think this is a very big task. We just have that the semantics of our language have to be compiled to some graph data structure. And we can hopefully use the target language of Quantumatics QGraph format, which we can then port to PhysX and wherever we want to go from there. So to conclude what we have presented here, the Zeta calculus is in some sense an attempt to capture the ZX calculus as a functional quantum programming language. We think non-linearity makes these languages more expressive. And we think that the quantum programming techniques that we found here are quite interesting. They are able to construct, for example, the C0 gate in a very minimal language, which was surprising to us. We can extrapolate on this and create entanglement and control entanglement in an interesting way with linking functions. We think basis dependence, this fact that you can introduce variables in zeta abstractions, so zeta of x and psi of x, is an interesting way that we can reason about how to integrate complementarity into quantum programming. And higher order functions, when shared, like we said, do not act classically, but we can use them to create functions which modify functions in some interesting way. And we need to have further work with the dagger functor to be completely satisfied with this language. Thank you.
All right, thank you very much, Nicklas. People in the Zoom, you can use the clap icon thing, reactions, if you want to clap. Do we have any questions from the audience?
Yes, I have a question.
Yes.
Thank you very much for the talk. I wonder when you talk about the derivation diagrams, you have this sequence of derived steps. And let's suppose that you have we fixed the starting point and the derived diagram. Do you have any intuition of finding different ways to derive the diagrams, or like a more efficient way to derive the diagrams?
This the type system that we presented was not in the syntax directed form. And the difference here would be that in the syntax directed form, we have to prove that different derivations are equal, at least, which is not something that we can show directly from the form that we presented now. But I'm not sure if we can reason about which is the most efficient way to derive the diagram, but we can at least show that they are equal. And this would have to be done with the rules of the string diagram language. But the starting point would always be the same, because the outermost term is the same, I think.
Right, then how would you show two diagrams that look different actually have the same semantics?
You would look at that going from some certain rule or some certain term structure by structural induction on the syntax, that if two different steps are to be taken, then you reason quite abstractly that you can go from one to the other with the string diagram language rules.
Thank you.
Yeah, do we have any other questions from the audience? Right, so let me maybe ask a more conceptual question. So the idea here is to like see select diagrams as programs, right? Like you're making a program, and then I guess the semantics is then linear maps. So it's kind of like a functional programming way to describe linear maps, I guess, would be one way to see this. Is that correct?
Yeah, or like more generally, of course, it's the morphisms of this category which happen to be linear maps. But yes.
And then what would a rewrite rule be? Would this be like a compiler step that is sort of like changing your program but preserving semantics?
Yes. So in the thesis, we have defined a set of a reduction relation. So the rewrite rules would just be the symmetric closure of that relation. So we have defined a set of rewrite rules with this term of commutation with sharing, and that is preserves semantics over these rewrites. But the hope then is that with the dagger functor, we can integrate more the ZX equational theory into this. Whereas now we have reasoned more on the basis of the internal language itself and building from that.
And so does that buy you anything sort of formally? Like if you were to say, try to make a formal language for ZX, the fact that you have this this description of a diagram, does that make it easier to sort of say these rewrite rules more formally?
In some sense, you get kind of the reasoning power that the lambda calculus has. You can prove these typical theorems of normalization, Church-Rosser, stuff like this. You can state it in a different way.
So may I ask, like in the conclusion, you mentioned that you would be curious to combine the this programming language description with the graph-like data structure. Could you give an example of like what do you mean by this?
Yeah, sure. So the semantics, we produce these diagrams, right? And they're defined by induction. So the idea would be that, for example, if you write this in Haskell, then we would have some data structure which represents the parts of the diagram. So for example, horizontal composition would be one constructor, and vertical composition, another one, the cups and the caps and the wires. So we just, when we have implemented the semantics of the language going into some graph or diagram, then we can map this to that data structure by looking at the diagram produced. And then from this diagram, we hope to be able to write it in some familiar file structure, such as the QGraph format of Quantumatic would be fitting, which we can then use to coupled with physics and OpenCASM and whatever.
Right. Like this is very interesting because Peter Salinger has this quantum programming language like package called Quipper, and it is also written in Haskell. So I wonder, have you looked into like if it's possible to basically code up this Zeta calculus representation in Quipper, because they had this like feature built into Quipper such that they could allow Quipper to talk to OpenCASM. And if you already have this beautiful language, I wonder how feasible or compatible it is with Quipper.
I'm not sure if I haven't looked too much into Quipper. I've looked at the kind of beginnings of it with the quantum lambda calculus, but the type system would be linear, and you might be able to write it then if you, in some sense, code it as a data structure. I'm not sure if you can define data structures like that in Quipper.
Right.
I think the simplest thing would be to write a compiler for it in Haskell. But then, of course, through physics, it could go to Quipper in the end.
Mm-hmm.
So one more question. So the construction you gave, for instance, the C-not gate, this is based on specifically having a cup that's connecting this, like I said, an X spider. This is just one way to represent the C-not gate. There's, of course, many ways.
Yep.
But these symmetries, they're not an inherent part of the way you describe things, right? There's like this would have to be imposed additionally via an equational theory, saying that like these two diagrams that are actually equal up to, like, you can see they're equal, like shifting stuff topologically, that this would be like an additional set of rewrite rules on this language. Like, is it easy to represent this kind of like topological rewriting?
Oh, I'm not sure about the topology itself. The way we reason here is, of course, simply on the ZX diagrams produced themselves. We kind of hijack the equational theory there to say that this is a C-not gate.
Yeah.
This is something that we didn't really have time to investigate in the master thesis.
Mm.
And this would also be related to this reduction and equational theory.
Yeah. Yeah, because that would also make it, like, for instance, spider fusion is just like, if you view it as a graph, it's really just one rule, but, or like a family of rules based on generators. But if you don't have topology, it becomes way more rules because you have to take into account every possible input-output combination and stuff.
Mm-hmm. I think we reasoned about fusion some time ago, but that is sort of when you place it would look something like this, but that you have these variables in the same basis, right? That in some sense creates fusion. So it would be reasoning about these Zeta abstractions themselves and how variables connected in different ways create fusion.
Do you have any more questions from the audience? Then, if not, let's thank our speaker again using the emoji. Nicklas, thank you very much.
Thank you.
For your talk. Yeah, so